These four factors are related to a basic law of electromagnetic induction, known as Faraday's law. This law states that the voltage induced in a conductor is directly proportional to the speed at which the conductor cuts the magnetic lines of force. This law is the basis for the design of the electric generators in use today. Let's take a closer look at how a generator works.
Generators are one of the most common sources of electrical energy in the United States. As an example, a gas-driven electric generator may be used on a construction site or on a pleasure boat to provide the same kind of electricity used in the home. An electric generator is a mechanical device that converts mechanical energy into electrical energy. The mechanical energy can be provided in different ways. Generators may be powered by the wind. There are many places in the United States where wind-driven generators, each connected to a large windmill-type blade, are used to create electrical power. Electric generators may also be powered by water. These are located at dams, which form artificial lakes. Water flowing down through tunnels in the dam toward rivers produces the energy needed to rotate large turbines, which in turn provide mechanical energy to several generators located within the dam.
In order to better understand how AC current is produced, let's look at a highly simplified version of an electric generator.
It's made up of a coil that revolves between the poles of a horseshoe magnet. Notice that the coil has been colored green at one end and yellow at the other to keep track of their position during rotation.
Let's slow one revolution of the coil way down to see how it interacts with the magnetic field through which it's traveling. Although it'll be stopped in certain positions, you must remember that in order to generate AC, the coil is constantly spinning.
As the coil revolves through the magnetic field created by the two magnetic poles, it cuts through the flux lines at different angles. To start, the coil rotates to a horizontal position with yellow on the left and green on the right. This graphic shows that for this instant, the coil is positioned parallel to the magnetic lines of force as represented by the arrows. At this point, no voltage is induced because the magnetic field is not being cut. But now, as the coil moves clockwise, it cuts through the flux lines at an increasing rate. At the instant that it reaches a vertical position, the coil is perpendicular to the magnetic field, which means that it's cutting the maximum number of flux lines. Here, the voltage induced by the generator is at a maximum. As the coil rotates further, it moves back into a horizontal position. As it does, the coil cuts fewer and fewer flux lines. Once again, when the coil reaches a position that is parallel to the magnetic lines of force, no voltage is induced because, for this instant, no flux lines are being cut. But notice at this point that the coil has rotated 180 degrees, or a half circle, from where it started. Now the yellow end is on the right and the green on the left. It's important to realize that proceeding from this point in the rotation, the yellow end of the coil will now be cutting the magnetic field in the opposite direction. From an earlier demonstration, you'll remember that when the magnetic field was cut in the opposite direction, a voltage of an opposite polarity was induced. It's this principle of AC generation that creates its alternating aspect, where polarities are reversed. As the coil rotates further into a vertical position, it once again cuts an increasing amount of flux lines until it reaches a point where the maximum amount of voltage is being induced. Finally, the coil rotates back to the original position where the coil is situated, parallel to the flux lines, and no voltage is induced.
This simple procedure demonstrates the fundamental principle of all AC generators.
But remember that a magnetic field surrounds the conductor in which the current is generated. This magnetic field is such that it opposes the movement of the conductor. It produces an opposing or counter-electromotive force, abbreviated CEMF. This principle is reflected in Lenz's law, which states that a counter-electromotive force has a polarity that opposes that of the source that created it. Because of this principle, it takes a great deal of power to drive a generator while it's producing current. The greater the current produced, the greater the power required to drive the generator.
Stop the program and complete activity number 3. When finished, continue watching the program.